11th Standard Mathematics, 3rd Chapter Trigonometry, Exercise 3.1, Question number 4. Welcome to the Explainer. Today we're taking this specific problem, putting it up on the board, and we are going to completely crush it together.
So, look at the question we're dealing with today. If sine theta plus cosine theta equals m, prove that cos to the power of 6 theta plus sine to the power of 6 theta equals 4 minus 3 times m squared minus 1 whole squared, all divided by 4. Now, I know, seeing that power of 6 can make your heart skip a beat, right? But hey, don't let it scare you. We absolutely do not back down from heavy equations. It might look like a heavyweight champion, but honestly, it's just a paper tiger. We're going to break this down step by step.
Here's our action plan, our battle plan, if you will. Honestly, it's super easy, just a basic 3-step process. Step 1, we expand what we're given. Step 2, we bring in a classic trusted algebra formula. And step 3, we substitute those values and conquer the right-hand side. That is literally the whole shebang. Let's get right to work. Okay, let's dive into this. Phase 1. We've got to start by squeezing the juice out of our given data. We're given that sine theta plus cosine theta equals m. Now, a little pro tip. In trigonometry, whenever you see a sine plus a cosine equaling a constant like this, squaring both sides is your master key. It's the move that opens all the doors for the rest of the problem. So let's write it out clearly here. Squaring both sides gives us sine theta plus cosine theta whole squared equals m squared. And you remember your basic algebraic expansion, right? Good old a plus b whole squared equals a squared plus b squared plus 2ab. Applying that exact logic right here, our left side expands beautifully into sine squared theta plus cosine squared theta plus 2 sine theta cosine theta, and all of that equals m squared.
Now, look closely at that first part. Sine squared theta plus cosine squared theta. You know what that is. That's our absolute golden identity in trigonometry. It always equals 1, no matter what. So our equation simplifies instantly to 1 plus 2 sine theta cosine theta equals m squared. Now let's just rearrange this to find the exact value of the sine theta cosine theta part. We just move the 1 over, so it becomes m squared minus 1, and then we divide the whole thing by 2. Boom! Sine theta cosine theta equals m squared minus 1, all divided by 2. Keep this result safe in your back pocket, guys, because we're absolutely going to need it later.
Let's move to and see how this builds, as it's time for phase 2. We're going to tackle that intimidating left-hand side, the LHS. It reads cos to the power of 6 theta plus sine to the power of 6 theta. It's time to transform this base into something we can actually manage. So, how exactly do we handle a power of 6? Well, we outsmart it using the simple laws of exponents. We can just rewrite that power of 6 as cubes of squares. So cos to the power of 6 becomes cosine squared theta whole cubed, and sine to the power of 6 becomes sine squared theta whole cubed. See what we did there? We just turned a scary high-level trig problem into a simple algebraic puzzle. Now, what's really interesting about this is how we build an algebraic bridge. We are literally connecting Chapter 3 trigonometry right back to Chapter 2 basic algebra. Take a look at this classic formula. A cubed plus b cubed equals a plus b whole cubed minus 3ab times a plus b. This formula right here, this is our absolute secret weapon for solving this. To make this perfectly clear, let's map out our terms so there's zero cognitive overload. In our algebraic formula, a is going to be mapped directly to cosine squared theta, and b is going to be mapped to sine squared theta. Simple as that, right? We're just going to take these specific trig terms and plug them right into our algebra formula. Let's write out that substitution step by step. Applying our a and b terms to the formula, we get cosine squared theta plus sine squared theta whole cubed, minus 3 times cosine squared theta times sine squared theta, and all of that multiplied by cosine squared theta plus sine squared theta. Okay, I know, it looks like a really long, terrifying line of math, but watch closely what happens next. So the crucial point is, look at those terms inside the brackets. Cosine squared theta plus sine squared theta. We already established that this is our golden identity. It's just 1. And because of that, this massive equation just collapses beautifully. That whole cubed term, it's just 1 cubed. And that huge chunk at the end inside the brackets, it's just multiplied by 1. Magic, right? Which leaves us with a beautifully simplified left-hand side 1 minus 3 times the square of sine theta cosine theta. Take a breath here. Seriously, if you've tracked with me this far, you are doing brilliantly. The hardest part of the logic is totally over. We are cruising now.
Now we enter phase 4, the final substitution. Remember that result I told you to keep safe in your back pocket back in step 1? Well, it's time to bring it out. We squeezed out the fact that sine theta cosine theta equals m squared minus 1 all over 2. So let's enthusiastically plug this exact value right down into our simplified left-hand side. Here is where we execute the final fractional math. Walk through this with me, line by line. First, we substitute. We get 1 minus 3 times the bracket m squared minus 1 over 2 whole squared. Next, we apply that square. The numerator stays as m squared minus 1 whole squared, but squaring that denominator of 2 gives us 4. So we're looking at 1 minus 3 times m squared minus 1 squared all over 4. To combine this into one neat fraction, we just take 4 as our common denominator. So that leading 1 basically becomes a 4 over 4. Putting it all together, we get exactly 4 minus 3 times m squared minus 1 whole squared, all divided by 4. And this brilliantly illustrates that we have arrived proudly and exactly at our right-hand side. We completely conquered the problem. LHS equals RHS, hence proved. We stood strong, broke it down into simple, bite-sized pieces, and just got the job done. So take a step back and look at what we just accomplished. We defeated a massive power of 6 trigonometry problem using literally nothing but basic algebra and a single trig identity. It really makes you wonder, what other scary trigonometry problems can you unmask with just simple basic algebra? I want you to go attack the rest of this exercise with that exact same unshakable courage. You've totally got this. Keep learning, keep pushing, and I will catch you in the next